All right. I think we're ready to go. All set. Hello, everyone. My name is McDonald. I'm a software engineer on the CCV. And today we're going to be talking about graph databases, particularly Neo4j, which is a graph database engine, and Cypher, which is the query language that can talk to Neo4j. So just to cover our bases, anyone's not familiar with what a graph is, formally, it's just a collection of vertices and edges, or informally, it's a set of nodes or things and relationships that connect to other things. So it's pretty basic. Why would you choose a graph database? Well, they naturally represent the data we see in the real world, from ecosystems to organizational hierarchies to our social connections. This is a natural, intuitive way to represent data versus, if you're familiar with relational databases, which kind of put everything in a tabular form, in a spreadsheet form, it's not really an intuitive way to store and represent data that has this relational quality. That's kind of the ironic part of relational databases, is they're not very relational. So for domains, I don't know what labs everyone's coming from, but for domains where relationships are first-class citizens, meaning the relationships between things are just as important as the things themselves, a graph database would be a great way to represent data of that domain. Next, it's flexible, it's schema-free. So to build a database, you kind of have to know the schema of all your tables and how they connect, and get your primary keys and your foreign keys down. It requires a lot of complexity up front just to get something built and going in a structure where you can store your data. Graph databases are much more flexible. You can, we'll get into it, but it's very easy to create nodes of a certain type, create relationships, and naturally your data is going to evolve over time. And it's really easy with graph databases to change the structure of the graph as time goes on. And lastly, and we're going to cover this in a little more detail, it's optimized to follow relationships directly and deeply. So if we're interested in how our data is connected across multiple relationships, we want to follow the edges of our graph. An example of this would be like if we wanted to know the friends of someone's friends in a social network, following the relationships directly and deeply. This is really, really good in graph databases. In a relational database, not so good. So on the left, we have a relational database. We've got two tables for people and friends. People has an ID, a unique ID and a name. Friends has some mapping between an ID and a name of their friend. So this is what maybe a relational database structure would be like for a social network of friends. On the right, we have a graph database. And so it's much simpler. You just have a node for the people and relationships connecting them. So you might have a friend of relationship between Alice and Bob. And so if someone gave us the task of finding the friends of the friends of the friends of Alice, we'd be doing a lot of complex joins and searches back and forth through these two tables. It's not so bad when we only have 3 users in our social network, but as the data scales, as our user base scales, this problem is going to get more and more and more complex. So our join intensive queries are going to deteriorate with more and more data. But for a graph database, we can always find, if we find the node, if we find Alice, we can easily find the friends of Alice, and from there easily find the friends of the friends. So it's much, much more optimal and efficient when you're trying to answer these kinds of questions. Actually, I found this in a textbook I was reading through. Partner and Bukatic. They did a study comparing the performance of a relational database to a graph database, trying to find the friends and friends of friends at different depth links. So you can see, you wanted to find the friend of the friend, the friends of the friend, friends of a friend. Wait, I got that wrong. I'm confused now. If you wanted to find the friends of the friends of the friends at 3 depths, so I guess 3 edge links in the graph, your performance of your relational database really plummets at about that path length of 3 length. But for Neo4j, for graph databases, that performance stays pretty steady consistently as your records climb up to the million. So this database had 1,000 users and 50 friends per user. So this really demonstrates how for join intensive queries, your performance is really going to deteriorate for relational databases. All right, so what is Neo4j? Basically, it's a label property graph. So we have our graph models we showed earlier. The only difference or what we would add with Neo4j is that each node has a label, and it can have a group of key value pairs for properties. So essentially, a node's going to have a type, and then properties could be characteristics that define the node of that type. Then you'll have a relationship, which also has a label of the type of relationship that connects a starting and the end node. And a relationship can also have properties as well. So this is all that a graph database, all that Neo4j represents. The underlying storage, so if we want to think about how the data is stored and give you a peek into the database internals, it uses a native graph storage. So it's not doing, I guess it's not lying to you. It's not like on the surface, it pretends like it's a graph database, but in its actual storage implementation, it's a relational database. It uses native graph storage, so it's optimized for graph data. The way it does this is it has different store files. So it has a store file for nodes, a store file for relationships, store file for properties and labels. And these all have fixed record types. And inside of the record type, you'll have some kind of pointer or offset into the relationship store file of the relationship that connects a node to another node. So in constant time, you can jump from one node to another. It's just a constant, lookup operation in the store files, which is really neat. And the processing engine is going to use index-free adjacency. So if we want to get to one node, if we want to find all the adjacent nodes, we don't have to create an index as we would in a relational database. The nodes have pointer-like references in the store files to their neighbors. So they physically point to their neighbors, which is really good for performance. Neo4j supports all the CRUD operations that are normal. What we think about read, write, update, delete. Hey.
I'm sorry, just on the previous slide, you said there's a pointer to what looks like the next property ID, but I can have an arbitrary number of properties per node. Is that correct?
Yes. I'm not sure what the representation of the properties file is going to look like. I know for, I didn't do much digging into that, but I know as a similar optimal lookup strategy that they're using. Here you can see that we get the relationship ID, which gives us an offset into the relationship source file, where we can jump and find, the first and second node that I guess ties this node that we're looking at to its neighbor node, and we can, I guess, easily traverse a node's neighbors like that. Like this is how it's doing it behind the scenes. But yeah, it's an interesting question of how it's storing properties.
Because if you go, so the property is like another stored list or another stored
File.
Yeah. If you want the node's properties, you do that. You move the pointer over 5, and then that takes you to the store files. But you probably have to specify the number of properties. Like if you want like 10 different nodes properties at 10 different positions, that probably gets
Yeah. I mean, the good thing is we never have to worry about this. Like we trust that Neo4j is like optimally doing this behind the scenes. I guess purpose of this slide was just to show how we can in constant time find the neighbors of a particular node, since we have these fixed records in store files.
If a node has multiple relationships, what does the next relationship ID exactly mean? Like for the node file? At the first like next relationship ID.
It's a great question. Yeah, I'm not sure. I can't answer that with confidence. Yeah, should good. But we'll move on. The processing engine gives us index-free adjacency. So nodes are physically pointing to their neighbors via the stores file. It acts just like a database where we can, create data entries, we can read them, we can update them, we can delete them. And it's going to comply with all the ACID guarantees for transactions that we're worried about. So it gives us atomicity. So every transaction that we make, every operation that we make to the database, if it's not completely successful, it's going to fail. Consistency, tells us that the database is always in a valid state. Concurrent transactions, so concurrent, reads and writes to the database aren't going to interfere with each other, and they're not going to read each other's writes. And then we get durability. So Neo4j maintains write-ahead logs. So if the node running the database fails, we can always recreate the database or the transactions that had completed. So I'm going to show you the Neo4j desktop. I think this is a really cool developer suite. So what I've been playing with is the desktop, the visualization tool, and then they give you a browser where you can actually run Cypher queries to the database. So this kind of gives you a dashboard of all the databases you have. So I've got a few here. And then there's all of these graph apps that you can use. So Bloom is a visualization tool. I haven't played around with charts, the data science playground. I've heard that the data science playground gives you a lot of, graph algorithms and models that you can run on your graph database, which is really neat. And so I can show you. So this is the desktop dashboard. This is the browser. So we can select a database that we want to run Cypher commands on, and then, run them here and see the updates, what changed. So this is a really, I think, nice user-friendly feature of the database, and allows you to sort of, get something going pretty quickly. And again, Bloom, which we'll look at later, it's a visualization tool. So you can, see a overview of your graph. I don't know if y'all can see that. And you can filter on nodes and different relationships. So I think it's really useful. Okay, so now we're going to talk about Cypher, the graph query language. So this is how you read and write to your database. So the Cypher philosophy, it's, I think, really cool and really easy to work with. It's a declarative query language. So you just specify the pattern that you're looking for in ASCII art. So if you're wanting to, find a node in the database, then you represent that by parentheses, and we'll look at this in more detail in a bit. If you want to connect a node via relationship to another node, you want to find like all the node relationship node pairings of a certain type, then you can use this dash bracket dash arrow to make that connection. Node relationship labels are prefixed by a colon, and properties are defined by the curly brackets. So this is an example of a pattern in Cypher. So if we first want to start this off with a node, so we're going to find all of the patterns, I guess, or all of the node relationship node instances in the database that match this pattern, which is what we're trying to do. So we start with a node and we specify the label. So we give it colon person. So we want to find a relationship that starts with a node of type person and has the property name Alice. So that's pretty simple. And then we specify the relationship. So we want to find if Alice knows another person named Bob. So compared to SQL, I think this is much better, especially when you get a handle for it. You can just specify exactly what you're looking for, and Cypher will go and find those nodes and relationships and return those to you. So it's kind of like a regular expression in a way for a graph database, which is really interesting. Any questions? We're going to go into more detail on this and give some examples, but hey.
We have multiple, properties like create matches and create something. So how can we like put multiple properties there?
Yeah, so this is just like, think of it as like a dictionary of key value pairs. So you could put a comment, throw in another, property value name. Yeah, good question. All right, so if we wanted to match all of the nodes and relationships in the graph, this is the pattern that we would use. So we're just saying, give me all nodes connected by relationship. We want to get more specific. If we want to find every person node that's connected to a city node, then we use this. Again, match is essentially like, you can think of it as get. We're gonna, we want Neo4j to return us all of the nodes that match this pattern. So any person node connected to a city node, it's gonna give us that back. And again, we can assign labels to these nodes because we'll probably be writing these Cypher queries in a longer file, and we might want to update this node or look at some property value of the node. So these variables give us sort of handles on these objects. We'll get a better idea of what that looks like in a bit. We can do the same thing for relationships. So we can assign variables to a lives-in relationship. Relationships can have properties as well, just like nodes. So this is going to give us back all of the person nodes that live in Providence. So this is going to give us back all the people that live in Providence. Any questions on match? Great. So if we want to create nodes or relationships in the database, we use the create keyword. And again, we use the same, representation that we use for match. So here we're creating the university node, Brown University. Then we're creating a department node, CCB, and then we're connecting these two. So we create two nodes, and then we make a connection with the variable names between them with the relationship department of. Does that make sense? So we create these nodes and we get a variable name, gives us a handle to reference that node, and then we can make the relationship between them.
Question.
Hey.
Say you have a file with a bunch of university names. How do you ingest all that data using?
Yeah, we're going to see that in a bit. Cypher gives you some different ways to load data into the database, but you can ingest CSV files pretty easily. So if you had like a CSV file with all of the university names, that would be easy to do. There's a load CSV command that you would run. So yeah, we'll see that. Okay, some other Cypher basics that I want you to be aware of. There is a merge keyword, and this is probably what you'll be using most often instead of create. It's like a match and then a merge. So first merge tries to find the pattern of what you're trying to create in the database. If it exists, doesn't do anything, so you don't have to worry about creating duplicates. And if it doesn't find it, then it creates the pattern that you're providing. This is recommended over create. It avoids duplication, as I said earlier. But you do run into this problem that if one node exists, but the other doesn't, then the entire pattern's not matched and the full pattern is created. So you will get duplication in this instance. I don't really like this feature of merge, but there's a best practice way to avoid this. So if we go back here, I guess I have an example right here. So if we try to create an author Bob who wrote the book Graph Magic, then if there is an author Bob, but there's not a book Graph Magic, we've only matched, a partial portion of this query, then what's going to do is it's going to create a new Bob node. So we don't want that. We would get a duplication in our database. So the best practice is first to merge each node you're interested about first. So merge author Bob. If author Bob exists, then we won't recreate it. And then we merge the book Graph Magic. If it doesn't exist, it creates it, and then we make the relationship. And so we don't get a duplication of nodes in this case. So when using merge, it's best to create your nodes and then create the relationships.
Maybe you're gonna get this later, just help prefer, but these are directional links. And if I anticipate I'm gonna want to search for the authors of a given book, is the best practice to include all those directional backlinks when I'm creating, or is there something in the way of Neo4j works that like all that actually automatically?
Yeah, so that's a great question. I don't think direction would matter necessarily in this case. If you wanted to find, you said all the authors of a given book, right?
Yeah, like this looks like I'll do really well if I know the author and I want to find all the books they've written.
Yeah.
But if I want to go the other way, I can search over a bunch of books and for each one find its author. Is the way these are constructed such that inverse search actually I don't need to even think about as long as the links are there, or should I be creating maybe some directions that I want to search?
Got it. So you would essentially do like, you run a match command, and then you would say, just give me all of the nodes. So you would want to match the pattern you're requesting. So you're wanting to get all of the nodes that have this pattern. A wrote this book. So let's see. So this would give you all of the authors that wrote the book you're interested in.
Yeah, but I guess if I read it a slightly different way, is that performance, if I had a very large database, is that performance going to be substantially different than the performance of creating a richer graph than you do back then?
I don't know. I don't think it would affect performance unless I'm not thinking correctly about it. I mean, in our previous match, so if I didn't define A here, it's gonna look through all of the nodes in the database. And it's gonna look for all the nodes with a rote relationship going out. And then it's gonna compare all the ones it finds to the actual book name. So I could narrow my search to defining, we're just gonna look at author nodes. So this would help performance, but yeah, I don't think. It might help performance in this case if you do create what you're saying. If you maybe have links going out the other way, because then you can in constant time find that book node that you're looking for, and then get your neighbors pretty quickly. So I understand your question now. I think you're right. Yeah, you could easily create those backlinks. You can't create bidirectional links. In Neo4j, you can only create a unidirectional link. So you would have to create it going the other way. that answer your question? That was a great question. Yeah.
Contemplator make something vital. What's like the added storage can allow vital?
Yeah. One, you would have to create the relationship going in both ways. There's not a way to create it. Well, it's going to take double the storage. I would assume that, and the way I'm thinking about it is, yeah, I would have to think about that a little more, but I would think you would have twice as many relationships for those particular nodes. It's not smart enough to say, well, these are both, the same type of relationship. I'm gonna merge them into one bi-directional relationship. So it wouldn't take any optimizations there if that's what you're asking. We can also filter on the properties of a node as well. So there's two other useful clauses, where and set. So we can match a person and limit the nodes we are returned by saying where p.age is greater than 30, set p.status to old, I'm turning 30 this year. So this is a question on my mind. Yeah, so again, we're matching a person node, all the people, and we've given each node that we're returning a variable p, and we're checking its age property if that's greater than 30. So for all the people older than 30, we set their status to, tentatively old. Yeah, so where's how we, filter based on property, and set is how we could add properties to a node. Does that make sense? All right, there's a couple other basics that you might use. If you're querying a particular node a lot, a particular type of node, we can create an index on that label. So that means it's going to just speed up our lookup time of nodes in the database. So if we, go back to maybe this example, we're matching nodes of type person a lot, then we might want to create an index for for all nodes of a person label. So when we're finding nodes in the database, like our first node in our matching pattern, it's going to make that lookup a lot faster. We can also, in the same way that you do in relational databases, you can create constraints. So if we want all of our nodes of a particular label to have a primary key or a unique ID, we can create a constraint on nodes of a type label and assert that the ID is unique. And so as we're creating the nodes in our database, this will allow us to maintain that there are no duplications. All right, so we're gonna kind of have a thought experiment. Say that someone came to us and they said, all right, we want you to build some kind of data storage system where we can query it for recommendations for what to plant in our garden in a given season. So they give you these use cases. They tell you, I want the database to be able to represent this kind of data. So if I should be able to ask the database, what native plants should I plant in New England in April to support pollinators, or what trees grow in northern Appalachia that support both chickadees and rosy maple moss, or which perennials thrive in this hardiness zone and bloom in summer. So we have some pretty complex queries and complex relationships in these questions. I think to sit down and actually write a relational database schema that represents all of this would be very tedious and take a lot of time. But with graph databases, I think it's a lot simpler, at least to get an instance model up and running where you can actually, I guess, flesh out what your stakeholder or project lead is asking you to do. So the way we start building a graph database is we start with the use cases. So we're going to model in terms of what our app needs. And so we write these sentences out, and then we're going to highlight or circle all the nouns in the sentences, and we're going to underline all of the verbs. And that's going to give us a sense of what type of nodes and relationships our graph database should be concerned about. And so we have plants, we have New England, so a location, we have April, which is just some point in time, and then we have the actual verbs plant and support. Again, you can read through these, and then you can start sort of creatively thinking what kind of nodes should be in my database, what kind of relationships connect those nodes. So next we're going to determine node labels from the use cases. So these are going to be all of the initial types for our graph database. Might have a plant, might have a pollinator, bird type, a region type, and a time. These will all have properties. So a plant is going to have a name, it's going to have a bloom start and end. Time, it's going to have a hardiness zone, maybe growth habit and nectar value. There's all these things, all these properties and ways that we could define each given node. A pollinator could have a migration start and end time. Same with a bird. Region's going to have a name, maybe a climate zone, a hardiness zone. And a hardiness zone is just like it's like I think 0 through 10 measurement, and it's just measures like the coldest freezing temperature that's possible in that region. And then you might have some sense of time. So next we look at our verbs, and we start to think about what our relationships might be, and we determine the relationships from the use cases. So we might want to have a relationship like a plant grows in a region, it blooms during a certain month, a pollinator migrates during a certain month, birds migrates during certain months, a pollinator feeds on certain types of plants, pollinates might have been a better relationship there. And a bird might feed on plants or the fruits of a tree. So we start fleshing out these relationships as well. So next we start collecting data, reflecting our nodes and relationships. So I've collected a CSV file for each node label type. So we have a CSV file for plants, for birds, and then we have a relationship CSV file which sort of relates the bird plant relationships. And so each CSV file is going to have a plant ID, a name, all the properties that we've decided are useful. And then the relationship CSV files are just going to be a mapping between the bird and the plant, or whatever the node types are of certain labels. So next, I guess the next step is to load our data into our graph database and actually create the nodes and relationships. So this is where we start writing some Cypher code. A good habit is at the top of your Cypher query file is to have something that deletes all of the nodes in your database. So here we're just matching all of the nodes of each type, and then we're running detach delete. So that's going to not only delete the node, but also the relationships that the node has going out of it. And then next we use the load CSV with headers file. So we're going to point whatever files we have, our CSV files, to the load.csv. We're going to give it a variable of row, and a field delimiter. What this is like, what are our I guess, what character separates the actual values in our CSV file. In our case, it's going to be a comma. And so this first section is importing all of the plants, creating those plant nodes and setting the properties. So this is our CSV file that has all of our plant data. We're creating a node using the merge keyword of type plant. And we're going to go ahead and put the property value plant ID as the row.plant ID. So again, row is sort of the object that represents our row of data in our CSV file. And then we're going to march down through all of the different properties that are, in our row object and set those to the actual node. And we're going to do this for each node type. I also want to show you let's see. Let me show you what what it looks like creating relationships as well. So this is creating all the relationships, if y'all can see this, between pollinators and plants. So this is creating a feeds-on relation between plants and pollinators. So this reads in the pollinators plant CSV file. It's going to match all of the pollinators in our graph. So we've already put all of our nodes into the graph. At this point, we're just creating those relationships. And so we're going to find all of the pollinator nodes in our graph database that has this, a certain pollinator ID. And then we're going to match the plant with the plant ID that's in our CSV file as well. And then this is where we actually create the relationship. So we've defined variables that reference, all those nodes that we're interested in, and then we create the relationship using the Cypher syntax between the plants and the pollinators. So that's how you create relationships.
The guidance on deciding when something's a property or should be relation to some other node. You have bloom start property, but I could also have something that relation is bloom start to things.
Right.
What are the pros and cons of the property?
Well, you definitely don't want to mix. I've heard like one anti-pattern is making, taking your verbs and your use cases and turning those into node types. Maybe there's some cases that you would be interested in doing that. Again, you have to, I guess, look at your problem and think about how the graph database is going to be looking up these nodes for the queries that you're interested in performing. I don't really know if there's one size fits all answer for how to determine between what should be a node versus a relationship. Like I would have to have an actual maybe use case. Can you ask your question?
Start.
Yep.
What would have been the consequence had you instead not have that as a property, but instead had a relation with start pointing to?
Yeah. Yeah, that's a great idea. I think that could, maybe be a better implementation of like our first pass at an instance model is to create, those relationships. But yeah, those are all decisions you'd have to make as you're building this out. Yeah. Yeah, I don't know. I guess I would be thinking about what type of like organization of nodes and relationships that would, for the types of queries I'm interested in performing on the database, what would result in the least amount of work for Neo4j. So in terms of the bloom start, bloom date, Yeah, I think it probably would be better just to have like a Bloom's start Bloom and it references like a month node. And then it ends Bloom referencing another month node. I think that would be better. It's probably redundant to store those as properties.
Is there a way to benchmark a model? Like maybe you kind of like define your schema or whatever structure. And there may be an alternate way to do the same thing. Is there an easy way within this framework?
Mhm.
Kind of like benchmark specific queries, decide which one is better?
Yeah, I think Neo4j does support versioning. So you could have like versions of your database in time. I'm not sure exactly how to do that. I haven't done that myself yet, but it does support that feature. So yeah, you could save off an instance of your database, rewrite your Cypher code that's loading in your data and creating all the nodes, and then you create a new version. It's definitely doable. All right, so what's next? So the last step would be just, to test the use cases. Again, we've gone from, having just our use cases to creating, doing some graph data modeling to actually creating an instance model with data in it. And now we want to test to see if, maybe one of the queries that our stakeholder gave us works, or something like it works with our database. And then we might go back and refactor, the structure or add some more data. But at least this is like a working prototype that we could show our stakeholder, our project lead, and say, hey, something works. Is this to make sure like it's in line with their requirements. So if we had the use case, what plants grow in New England that bloom in August and support pollinators, then this is the type of query that would be running. So if you read through this, we're going to match all the plants that grow in New England first, and we're going to save, a variable referencing those nodes. And then we're going to match the, pollinators that feed on the plant. So in this case, the link is going the other way. So we've got our plants that are in New England. Now we're going to find, pollinators that feed on this certain plant. And then we're going to see, which ones bloom during August. And what that gives us back for our, the little amount of data that we have is that the black-eyed Suzanne is, would support the Eastern tiger swallowtail. So, we have something working. I think this is pretty impressive. Like, this is much easier. If someone gave me this task to do in a relational database, I would be very daunted. I think writing the SQL to do something like this would be pretty gnarly. And yeah, I think it would take me this is much more intuitive to me than other query languages, which I like a lot. So are we on time? Okay, we got a little time left. Just going to show you how easy it is to, run some Python code that connects to the database. So here we have a very, short program. All you have to do to connect to your Neo4j database, again, you download the desktop, you can create some databases there, run some queries there to create some data. But if you want to actually, reference your database from a program, which is likely your intention, what you have to do is first do maybe create a virtual environment for all your dependencies, and you'll want to install Neo4j into your environment. So that would be as easy as, pip install Neo4j, which I've already done. So I'm not going to run again. And then Neo4j provides a driver class that makes it really easy to connect to your database. So Neo4j by default will start running on port 7687 on your local host machine. So that's where your database is going to be running. You can give it your username, password. I think by default it's Neo4j when you just create a database through the desktop. And then this is where we're actually running a simple query. So we're going to use the driver that we get back. This is our connection to the database. We're going to start a session with, I guess, the database that we're interested in. A Neo4j instance can have multiple databases running. So I guess the driver connects us to the Neo4j instance, and then we can select what database we want to talk to. And then we can actually use the session.run to run the query. In this case, we're just matching all the nodes and returning a count of all the nodes. So the current plant native database has, I think, 49 nodes total. So we could easily run that code and get back 46. I can't remember what Python calls this syntax here. But essentially, what this with clause does for us is it's going to close the connection to the database. It's going to context metric. Yes, thank you. It's going to run driver.close in the background, so you don't have to worry about it. If you didn't use the context manager, you would have to call driver.close at the bottom of your program just to close that connection with the database. All right, let's look at one more Python program. This one's a little more complex, but not too much. So in this case, we're going to pass a query with a variable that we're defining in our program to the database. So again, we're setting up the driver and the connection in the same way that we did in the last program. We're going to call session.one in the same way. This time we're going to pass in, first parameter is going to be our Cypher query. And then the next is going to be the parameter that we want to pass into our query in the database. So what this query is going to do, it's going to look up a particular bird that feeds on a plant. So our variable here is the American robin. We're just going to see what plants does the American robin feed on. So a very basic query. This gives us back a red mulberry tree. So this is a way we could run queries from a Python program, but also pass in parameters that might be coming from like a user prompt or some user interaction from your application. Any questions on running queries from Python? Also, Neo4j has support for all kinds of languages, so you're not limited to Python.
The question showed how to ingest CSV files. What about export?
You might.
Can you repeat that question for Zoom? It was too hard to hear.
Yes, the question was, what if you don't want to use CSV? Probably a more like optimal input.
It showed that ingest data, but suppose I have graph database and I want to push it out of Neo4j.
Yeah.
For some reason to somewhere else. What are my exports?
Right. I'm not sure. That's definitely you could definitely, I'm sure, perform some kind of data dump on the database. Yeah, I'm not sure how to exactly do that, but I'm confident Neo4j gives that support. Yeah, great question. Let's see. I think that's it. So these were sort of the resources that I use to learn. Highly recommend these two textbooks from O'Reilly. And Neo4j actually has a Graph Academy where there's probably 30+ courses on there that will kind of teach you from the ground up, how to work with Neo4j and implement, I guess, connect from your programs and do everything that you would want to do with Neo4j. There's actually some interesting things that you can do with large language models as well. Like giving it access to your graph database and then just in plain text asking the large language model to generate a query for you. So it can kind of understand the ins and outs of your database and then write a search query on your behalf, which is, I think, really interesting. There's some other things you can do as well with large language models. So I recommend you checking out these courses and resources if you're interested. And I think that's it. Any questions? Thanks for coming. Okay.
Yay. There's still some pizza left over, so if you'd like to take some pizza, please do. And if you haven't signed in, please sign in. Thank you so much. Yeah, I think that's it. Great job, Ford. Let me see. I think the next one is April 11th. Is that correct? It might be a few weeks for the next one. Thank you for joining. Bye.